Good afternoon, people. So today we'll be talking about poles and figures, the math behind it. So what happens when we Google math and origami? Well, you get those images. You guys might call it beautiful, colorful, complex, beautiful. But when I say there's math behind it, most of you will want to run away. So what's the debate between math and origami? So purest origamists say origami is largely an art. Why do you want to put math into it and spoil it? Whereas purest mathematicians say origami math could be a recreational math, the one gimmicks used to wake up the backbenchers. But both fanatics clamor when you point out the most obvious simplest example of the connection between math and origami. Any guesses? Well, when you think of origami, you usually think of creases. And creases are usually straight lines. And straight lines are always 180 degrees, and 180 degrees are angle. And when you think of an angle, it's always math. Therefore, when you think of origami, you usually think of math. Right. So in the next hour or so, we'll be taking you to the presentation. It has 3 sections. The first section is on whether poles are actually useful in real life. Whether origami enables math and whether math enables origami. So the first section. Are poles actually useful in real life? So the first part is there more to origami? So do you do it just for the aesthetic beauty of the model, or do you do it for the kick you get in solving the puzzle? And where does the line between math and origami exactly blur? So in the next few slides, I'll be showing you some real-life applications of folding. So this is a foldable bus stop roof, and it's made out of folded wood, and it really reduces the time and cost of production. And it's very flexible and portable, so you can take it from one place to another very easily. And it's made from and the design is of a model called triangular spiral, as you see there. And it's a foldable beach hut developed by an NGO called origami. And this is made out of cardboard. It's glazed cardboard, so it's waterproof and flexible, and it's being distributed to the homeless in the US. And the thing about this is, it's got 2 points, very flexible and portable. So the thing is, you can increase the size of the hut depending on the number of people you have. And because it's cardboard, it's very light, so you can carry it around on your backpack. Yeah, this is the Yokohama International Pavilion, and it's also made by a similar design as the previous one. And that's an extendable bridge over the lake. So when the lake gets full, you can extend it and cross the lake using that. And any of you seen this folding before? Yeah, it's quite common on campus. Yeah, these are also temporary pavilions in Germany for shade against the snow. Yeah, and they are also made by a similar design. Okay, this is the Haori shelter, and it's inspired by the folded leaves of a hornbeam tree. So this is waterproof, and it's used a lot in Japan. And since it's very light and flexible, trekkers and disaster management people always use these. And the French use it for kids' play area because they've got a lot of privacy. And yeah, it's made using the Muley fold, which is again common on campus. Yeah, this is a model that is made by double arrow fold, and this is very strong, but at the same time it's very flexible, as you see how it becomes from one model into another. Okay, this is the origami inspired solar array. So when you want to send satellites into space, they need electricity up there, so they are solar panels, but those are very big. So you need to condense it into something much smaller and then send it up there and open it up. So you condense lenses and solar cells into something small using origami, and NASA did that and sent the eyeglass telescope in space, and that's got a 5-meter radius, a 5-meter diameter, and the man you see there is Robert Klein. He's a scientist at NASA as well as a renowned origamist. Okay, and coming back to Earth, these are other few applications of origami. So people realize that when you fold paper parallelly, it increases the strength. Whereas if you make intersecting creases, it increases the strength of it increases the weight and endurance of the paper. So like the bench you see in the top right, it can accommodate 8 people. Okay, this is a foldable chair from China. So it uses origami to make it flexible and strong, and it can be put into various shapes, and it can be folded into something small and carried around easily. These are folded bamboo houses. They are intended to be used as temporary shelters. Japan uses them because there are a lot of earthquakes, and these are parabolas in them, which make them very stable. And this is also quite common on campus, as you see Kalshuram holding this parabola. There. And not very long back, there was a man who used to go kayaking, and he got an apartment, and he didn't have space for his kayak. So he used origami to fold the kayak into something as small as a suitcase, and that's how it works. Now I'll hand over the presentation to Freya for the next section.
Now we have seen the application of origami in life. Now we'll talk about how origami helps math. So in 1893, Indian mathematician published a book called Geometric Exercises in Paper Folding. So this book used paper folding to demonstrate proofs of geometrical constructions. This was the first time that idea of origami and math was explored, and the book was first of its kind. Here, he was inspired by the use of origami in the kindergarten system by a German educator called Friedrich Frobel. And this book, it had an approximate trisection of angles, which is not possible using Euclidean geometry. That is, you can't use a compass and a scale to trisect an angle. And it said that construction of a cube root was impossible, which is not true, as in 1936, a lady called Deloche showed that the use of Deloche fold could allow the geometrical equation to be solved using origami. Deloche fold is basically when 2 points on one side are made to meet 2 independent points on 2 parallel lines simultaneously. So as it's shown in the picture. And as the idea popularized, in 1989, the first international meeting of origami science and technology took place. It was held in Ferrara. It's called OSMI, and it's been happening annually ever since. So this was at a very general level to something more nearer to us. This is a program called Origametria. This is used to teach geometry through origami to children of ages 5 to 12. Basically, it was created by the Israel Origami Center, which was started in 1992 by Paul Jackson and Mary Golan. So it emphasizes on the following skills, and as research proved that this way of teaching origami is better, this way of teaching geometry is better than teaching it the conventional way. The Israel Ministry in 2008 took up this formally. So it's mandatory for all public schools to teach geometry this way. And presently 70 Jewish, Arab and Christian schools are being taught using this. Now, answer the paper. So, or if you can just take a paper. Don't take the colored papers, take the rough paper.
So